think some of you are still getting used to the idea of how you build these trees up. If you remember, we start with what we want to prove. We kind of go up. We build more and more of the tree until right at the leaves there are very simple things that we've actually already, that we can actually prove, and then we go back down to get the answer. So of course here we have the answer, but we're going to do that process. We need to go back up and complete the tree. Okay, so in order to do this, this is an application of this term to this term. So I need the rule for applications. And the application rule says, if I want to show f applied to A has some type tau, I need to show that f has type sigma arrow tau and A has type sigma, for some sigma. And I get to choose that sigma. So it's not a really ideal rule because it's not algorithmic. A computer couldn't execute this rule because we have to find that sigma. So it requires some creativity. It requires some extra input. How do you find that sigma? And so for us at the moment, we're just going to be super intelligent human beings that can work out what that sigma is. If you were to write an algorithm for computing types, you'd have to write an algorithm to find the sigma. Anyway, so this is the general rule. And in our general rule, that's our f, that's our A, that's our tau, and that's our gamma. So the gamma is empty, and that's because, remember, the context always tells you about what to do with the free variables. In reduction semantics, the context is telling you the value of the free variables. Here, we're doing types, so the context will tell you the type of the free variables. But in here, there are no free variables. That's why this context can be empty. Anyway, so now we can just apply this rule. So, I need to do two things. I need to find a type for f, and find a type for A. And the type of A must match the input of the type for f, and the output of the type for f must match the overall type that I'm looking for. So that tells me I can just immediately copy loads of stuff down. I need to show that f has type something, sigma. That's new, I don't know that, so I'm going to move along. Ignore that for the minute. Arrow and tau. Tau is this type here, and we know in our example that's n. Sorry, and that's not, of course, f. That's, oh, I've screwed it up already. That's lambda x, arrow x plus 4 must have type something arrow n. And I have to show that by A has the something type, which we don't know. We have to work out what this is. So our A is this. So I'm going to have to show that lambda x arrow 3 applied to 7 has some type. And that type will become my sigma. Okay, that's fair enough. So let's do this one again. Let's do some more work on this. So now I've got to work out what is the type of lambda x arrow 3 applied to 7. I use the same rule again. So I need to know what is the type of lambda x arrow 3, and I need to know, that's type something, and I need to know what is the type of 7. But I know what the type of 7 is, that's a number. So this has to be n here. Okay, so that's the type of the input to this function. So this function type, its input must be the same as the type of, the input of the function must be the same as the type of the input. So I've written n here, I've got to write n here. Okay? Now, how do I work out the type of this function? Or indeed, how do I work out the type of this function? I need the rule for functions. So I'll write that down for you, and I'll try and get on the same page. I'll write it here. So I can show that a function, lambda x arrow t, has type sigma arrow t, if I can show that when I take x to have sigma, so I extend the context, then t has type tau. So this is the rule for functions. I've got two functions I need to type, so I'm going to use that rule in these two situations. Okay, so let's have a look at this rule. So if I want to type lambda x arrow 3, well, I need to take my original context, which is empty, and put the bound variable in the context. So x is going to have some type. Well, what is this sigma? Well, this sigma is the same as the input to the function type. But I know that. That's a number. So that's going to have to be n. And then I'm going to have to show that 3 has some type. But I know the type of 3, it can only be the natural numbers. Which means this has to be the natural numbers, which means that has to be the natural numbers. Okay? Now, again, looking at this rule, remember, I have to type this function, I have to check its input is the same as the type of the actual input. Has the same type as the actual input. I worked out that's n, so I'm going to have to show that's n. So I need to show this function is type n arrow n. How do I do that? Well, again, I use this rule. So my gamma is empty, but I'm going to extend the context with this variable being given the input type of the function. That's n here. So I'm going to have to write x is type n, and I'm going to have to show that the term t has type, the output of the function. That's n. So I have to show that. And to show us the rule for sums, so if you want to show that something plus something has type natural numbers, show each of them as type natural numbers. So I need to show x is type n, show proves x is type n, and show x is type n, proves 4 is of type n. And then the rule for variables and the rule for numbers gives you these. So that's the answer. That's both forms of the answer. It's first of all, it shows that this term has this type,